Okay, so what we are going to study today is the Gauss-Seidel method. And the Gauss-Seidel method is one of the methods of solving simultaneous equations. So there are three basic methods. Okay, so in case if you don't know, there are three basic methods. One method is what we call as the first method that we actually extend for learning is the Gaussian elimination method. So this Gaussian elimination method was taught to most of the students in school. So Gaussian elimination method. The first method is Gaussian elimination method. The second method is called the Gauss-Jordan method. So Gauss-Jordan. Okay. And the third method is the Gauss-Seidel method. So uh, in this lecture, what we are trying to do is understand the Gauss-Jordan, Gauss-Seidel method. So each of these methods are different from each other. Uh, what will happen is the Gauss-Seidel method is an iterative method, but it has got its problems. But it is the most applicable one to those people who are working in the domain of structural engineering. They will be made aware of the finite element method, and because of that, you will have mm, you will have the more utility. You have more applications of the Gaussian method compared to the other Gaussian elimination and Gaussian. So now the how does the Gaussian elimination method differ from Gauss-Jordan? How does it differ from Gauss-Seidel method? That also I will cover in brief. So let us try to do that. So if you remember in your junior classes, and I'm going to briefly do this, if you remember your junior classes, you might have seen an equation like this. So you might have seen say like 3x plus 2y, okay, and this is becoming, say for example, 8, right? And then you can have another equation where you have, like for example, 2x minus y, okay, and then you'll have 3. So there can be an equation like this, a set of equations. So remember in this particular set of equations, there are these variables x, and this variable is there y, and so therefore this equation, if I want to really write this in the matrix format, I can actually write like this. Okay, so in the matrix format, this can be written as 3 2 and 2 minus 1. Okay, and you can write it like this x and y, and this will be written as x 8 and 3. Now, one of the beautiful techniques in linear algebra is that I can actually come up with this solution that from here I can just come up with this, that I can write directly x and y, xy equals to, I compute the inverse somehow of 3 to 2 minus 1. Okay, I compute the inverse of this and then multiply this inverse with 8 and 3. So if I do this, this will be solving the equation of 8 and 5. Now, the problem seems very simple when the system is a 2 cross 2 matrix. Okay, it's a two variables, two equations, and the system seems very simple. But what will happen is whenever we are dealing with bigger simultaneous, how are you going to encounter such simultaneous equations is when you get into finite element analysis, you get into meshing, and where you have to, where there are multiple number of nodes, and it is quite possible that you will get a matrix of something like this is like 50,000 cross 50,000, and there you might need to find better methods of inverting uh, these matrices. I'm just saying 50,000, so I just wrote one thing extra. So there you have to find out methods, better methods of inverting these matrices. So in order to find these better methods, so some of the mathematicians did extensive work on finding inverses of matrices of very large matrices, and they come up with these three methods. Out of this, the Gauss-Seidel is the iterative one. So this is an iterative solution. So Gauss-Seidel happens to be an iterative solution. Iterative solution, what does an iterative solution mean? That you assume an initial solution, and from that initial solution, you go and converge into the matrix and go and converge to the solution. That's what I'm saying. Okay. So in the iterative method, you assume an initial solution. Whereas in Gaussian elimination and Gauss Jordan, there is no need to assume an initial solution in this particular case. So how does the Gauss-Seidel method work? So we will go and move into the how does it work? So working. So that's what I'm worried about is the working of this Gauss-Seidel method. So how does it work? Okay. So let us first of all understand what will be given to us. So what will be given is we will be given simultaneous equations. Okay. So there will be n equations, n variables. I'm not going to complicate this by adding more equations and lesser number of variables. Let us not do that. First of all, let us find out the solution where there are n equations and n variables. So we are going to be in that scenario where there are n equations and n variables. So let us write down some of these equations. Okay, let us see how these equations look like. All right. So the equations will look like this. So I'm going to use a different color. I'm going to apply. Okay. So first equation is a11 x1. Okay. So what I'm going to saying, what I'm saying is what are there are inputs in this particular system. So there are variables. Okay, these variables are represented as xi. So where I is from 1 to n. Okay, so there are these variables. Okay, and there are these constants. Okay, so there are these constants. So basically, we can call these constants as coefficients. Okay, and these constants will be written as aij. Okay, and there will be these results. So the constants are there aij, and there will be these results. So the results are written as p pi. Okay, and again I is from 1 to 2. So so there are n results, there are n variables, and there are constants. So I for constants I and j. So this will be from I equals to 1 to n and j equals to 1. So this is how it looks like. All right. So what we are going to do is write down some of these equations so that we can understand how this works. Okay. So let's see. So we are going to write down. So first equation is a11 and x. फिर उसके बाद a12. So it is the first row and second column. So I'm just writing a12. Okay, and so on so forth. It will go for a1n xn. Okay, and this result is given as b1. All right. So this is the first equation. In similarly, I'm going to write a21 x1. So a21 means second row, first column, a21 x1 plus a22 x2. Okay, and then we are going so on and so forth, a2n xn. Okay, and this will be written as b2. So similarly, on and so if I actually write the ith row, so it will be like this: ai1 x1. So I'm writing the ith row ai2 x2 plus it will go up to so ain xn, and this will be bi. Okay, and what will be the nth row? So I'm just saying this one was the ith row. And so I'm going to write the nth row now. So this is nth row will be a n1 x1, and we'll write a n2 x2 plus and so on and so forth. We are going to write a n n x equal to b. So what is happening here is there are these. So what I can write is very shortly. I can write here is there are n equations and there are n variables. So remember that the number of equations and variables must be the same in most of the cases. Okay. Otherwise, we have to use the least squares method. If they are not the same, and always remember that the number of equations must be greater than the number of variables, then only we can use the least squares method. So greater than equal to has to be there. Okay. So all right, so now this is how it is. What we have to do is rewrite each of these equations in a new format. It's a better format. So what I am going to do is I am going to consider this as the pivot element. So let me circle this out. So this A11 will be considered a pivot element. Similarly, I'm going to consider this A22 as a pivot element, AII as a pivot element, and similarly ANN as a pivot element. So here the assumption here. So I'm going to write this assumption. Is very important that we understand this assumption here, because if that is not true, then this system cannot be solved. The assumption here is AII is not equal to, or rather, okay. So okay. I will say not equal to 0. Okay, so this is the assumption before we go on and solve this problem. First of all, so now what we are going to do is rewrite this particular equation. Which particular equation? I'm going to rewrite this equation. I'm going to rewrite this. So if I have to rewrite the first equation, what do I have to do? So I'm going to rewrite these equations. So let us see how we rewrite. Okay. So remember that initially what is going to happen? I have been given A11, so I'm going to write the equation again. So A11 x1 plus A12 x2, okay? And similarly, I'm going plus plus, and then I'm going to A1n xn, and this is basically B1, okay? So what I'm going to do is it is equivalent to writing. What is equivalent to writing? It is equivalent to writing A11 x1 equals to, okay, and here what I'm going to do is, so because I have considered A11 as the pivot element, I am going to keep this on the left hand side and move all the other parts to the right hand side. This is what I'm going to do. So I'm going to say B1, and I'm going to say minus, and I'm going to say here it will become A12 x2. Then here we'll be having A13 x3, and minus, we'll go minus and up to A1n x. Okay, so this is what we are going to do. Okay, now what will happen here is that if I again rewrite this, I can write it like this: x1 equals to, see, 1 upon A11, and here what I'm going to do is I'm going to write B1 minus A12 x2 minus A13 x3 minus so on and so forth minus A1n. So if I do that, this is A1n x. Okay, so this is how we write it. And if I have to really follow the sigma notation, we will do it later. But anyway, so this is the first equation. When we rewrite the first equation, it becomes like this. So let us try to rewrite the second equation. How does the second equation look like first? So I'm going to write the second equation now. The second equation is looking like this. So we are going to say A21 x1 plus A22 x2 plus A 2, 3. So I'm just writing this x3 element so that we can be convenient. For the sake of convenience, I'm writing that. So xn, and that is equal to. Okay, so second row, the result is b2. And I'm going to rewrite this equation. And I told you earlier also that I am going to consider this particular A2, this A2 as the pivot element. So therefore, what I'm going to do, I am going to retain this particular thing in the LHS. Okay, I'm going to retain this in the LHS and remove all the other elements to the right hand side. So that is what I'm going to do. So what I'm going to do, okay, fine. So I'll just say equal to, okay, so we'll just go back to the original color. So here you are. So I'm going to write A22x2, okay, and that is equal to, now please be careful here, B2 minus, so remember A21x1. So now as A22x2 is on the left hand side, I'm not going to write this, and then we are going to say A23x3 plus, not plus, it should be minus, minus dot 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 minus A2n x. Okay, so this is how it is. And therefore, if I have to really find out the x2 from here, so the x2 can be found out by like doing like this. X2 is 1 upon A22. All right. So this is I have found out for A22. Now please see that for this particular x2, I have got the x1 element, the x2 element is missing, and the remaining. Okay. Fine. So what will happen for xi? Let us see what will happen for xi. So I can I'm trying to write in a different color. So again, xi, how does it look like? Let us see. So how is the equation of the ith equation? So ith equation is a I1 x1 plus a I2 x2. Okay. Sorry. Okay. Then we go so on and so forth up to a I xi, okay, plus you'll have a in xn, and that will be pi. Okay, so if this is the case, what is the pivot element here? Again, if I were talking about the pivot element, this happens to be my pivot element. Okay, so since this is the pivot element, I am going to retain this part in the left hand side, and I am going to remove all the other elements into the right hand side. So this is how I'm going to do. So what will happen here? So let us see this. So this will imply, okay, so this is basically implying that I'm going to write AII XI equals to PI minus. So AI1 X1 minus AI2 X2 minus so on and so forth up to AI minus 1 XI minus 1. Okay, and then it goes forward to xi plus 1. So you have got ai plus 1, xi plus 1, and so on and so forth to ain xn, and this will be it. Okay, so this is how it is. So if I have to understand this, it's very simple. This is how I'm going to do it. And so you can put a bracket here and put a bracket there if you want. And with this, I can actually write xi equals to 1 upon aii. Okay, and 1 upon aii. So, and then the same expression, whatever you have got here, the same expression you write up to this particular part. So the same expression you have got. Okay, minus ai2 x2 and so on and so forth up to ai minus 1 x I minus 1 and so on and so forth. So all that part you have to write it here. Okay, so including this part, let me see if this part also is going to come. Now once I have been able to do this, can I put a sigma notation? This is how, because ultimately you have to have a sigma notation. So this will become the generic expression for solving the problem, and the generic expression can for solving the problem. And remember that now what is happening here, one thing that I have to do before I am going to put the sigma notation first, and then I'm going to tell you the iterative factor, how the iterative factor actually takes part, okay, takes place. Right. So let us talk about the generic expression. So I'm going to write the generic expression like this. Okay. So if you look at this particular expression, how it is, and okay, so I'm just going to bring in some the top also. Okay. So I'm going to write the generic expression. So generic expression is like this. So I'm going to say xi. Okay, that's definitely true. Okay, we are going to write 1 upon aii. That is also true. Fine. That is also true. Now, what we are going to say, we are going to say bi. That is as it is. Now here you see the sum is going from I equal to 1 to I equal to I minus 1. You are going to see that. Now, so therefore, how do I do? I'm going to use a sigma notation. Okay. And I say k equals to 1 to I minus 1. Okay. And then here, what I'm going to do is I write a I k. Okay. And we are going to write x. Okay. Now, in this particular expression, what is going to come? In this particular expression, the things will begin from ai plus 1, xi plus 1. You see, it will start from xi plus 1 and then go from minus, minus, etc. up to ain xn. Okay. This is what is going to happen. So I'm going to let us rewrite this again. Okay. So you are going to write ain xn. Okay, I write like this. So what I'm going to do now, I'm going to write the remaining part of the expression. It is minus. Again, I'm going to say use the sigma k equals to I plus 1 up to n, and I'm going to write a I k is the same expression here, a I k x k. Now, I have been repeatedly saying that this is an iterative solution. I've been repeatedly saying that. How does the iteration take place here? So if I have to write the iterative expression, how do I write that? Let us try to write the iterative expression and therefore solve the problem. So let us do that. So I'm going to write like this. So the iteration is I am going to calculate the current value of xi. The current value of xi is calculated from the previous value of xi and the current values of xi. Both. Okay. So I am going to say if I am numbering the iterations with j, okay, if the j is the numbering, xij is written like this. Okay. The older values are written on this part. These will be the current values, and this will be the older values. That is what the understanding is. Okay, let me mark them with an old, different color so that you can understand well from the board notes. So these will be the current value, the current. Okay, so these will be the current values, and these will be the older values. And remember the why I'm saying current value and older value. You are going to calculate x1 first, then you are going to calculate x2 using the current value of x1. Then you are going to calculate x3 using the current value of x1 and x2, but the older values of x3. So this is how it is. So I am going to do this, and I am going to write this expression now. So let us see. So it is equal to 1 upon aii. I wrote 1 upon aii. Okay, and bi. So remember that aii, bi's, they don't change. They are constants, and therefore they don't change. But what is going to change is what is changing are the values of these variables. Okay, so and then what you have to happen is this aik, that also is not going to change. So xk, when I say current, it means they are from the jth iteration. Okay, and minus when I say old, it means from the previous iteration. So k is equal to I plus 1, and then I'm going to say n here. So I'm going to write aik here and xk, and these are from the previous iteration, so I have to write k. So this is what the understanding is. I am going to use at certain point newer values and at certain point older values. So this is how it is done as an iterative process. Okay, so we can, if I want, we can try to solve a Gaussian equation. Now remember one thing. Now one thing is very, very important. Why it is very important? Because if I don't consider this, the Gauss-Seidel method will not result in a solution. It will go on and on up to infinity. And this is a mandatory requirement in all the Gauss-Seidel based solutions. The Gauss-Seidel based solution is also applicable to this methods in structural engineering. That also has to be kept in mind. But what is the catch here? Please see what is the catch here. The catch is like this. Okay. So there is something called the concept. So I'm going to introduce the concept of what we call as a diagonally dominant matrix. So diagonally. So I'm going to say this concept of diagonally dominant matrix. And remember that there are two diagonals in any matrix because the matrix is the square one. What the diagonal I'm talking about is the principal diagonal. So let me tell you what this is. Okay, if I am going to write a matrix like this, A11, A12, A13, okay, so on and so forth, up to AN1, okay, sorry, not AN1, 1N. Just to forgive me for that. So that will be A1N. Okay, here it will be A second row 21, A22, okay, A23, and so on and so forth. And this will become up to A2N. Okay. And if I have to write the ith row will be AI1, AI2, AI3, and somewhere in between here will be AII. Okay, and here it will become AIN. Okay, and these are dots here, right? Remember that these are dots here. Are contents in between, so they don't. These are not blank elements here. So these are dots here, right? So what I am trying to write is a matrix system here. Okay, now at the nth row, this will become AN1, AN2, AN3, and this will be dots here, and then it will be AN. So this is how it is. And what diagonal I am trying to refer to, the diagonal I am trying to refer to is this element. So this is all these elements which are ending having the same subset. So A11, A22, A33, A44. AII and ANN. So these are the elements of what we call as the principal diagonal. So I'm talking about the fact that for using a Gauss-Seidel method, my principal diagonal has to have the biggest numbers in each row. So the biggest numbers in each row, that is what it is there. If I don't do that, remember that if I don't subtract from a bigger number, if I don't do a bigger number, what will happen here? Look at this. If this number is large, this number is going to become smaller, right? So if I've got a large denominator, the numerator or the solution is going to become smaller. But if I have a small denominator, eventually this can become larger. So this always remember this basic arithmetic that I have. If I have a bigger denominator, this is going to be a smaller number. If I've got a smaller denominator, this is going to be a larger number. And so it should not lead into any confusion. So that's the reason why is it has to be a diagonally dominant matrix. It is a mathematical requirement for all the equations here. Okay, so I can with the Gauss elimination sorry, Gauss-Seidel method, I can try to solve, like for example, I can try to solve this an equation of this type. Say for example, I've got 10x minus 3y, okay, plus z minus w equal to say for example 12, okay, and then I write, then again I will write say for example 3x minus 14y, okay, plus 5z, okay, minus 3w equal to 13, for example. Okay, I can keep us. So basically, what is going to happen here is these elements. So here maybe a some big number here, 15z, and maybe another big number here is say 20w. Okay, so these numbers have to be the biggest in the row. If I do that, then only I can solve the equation by the Gauss-Seidel method. Okay. And now let me also tell you that you can solve the Gauss-Seidel method. So what you can do is let us try to write down a system of equations. We'll write down a system of equations and we'll try to solve that system of equations in the spreadsheet. We'll try to do it in the spreadsheet so that we get the solution and it should easily converge because somewhere you need bigger solutions. So how do I start solving? Well, my first question is how do I start solving? So okay, so let us remove everything here. So how do I start solving? So at the initial level, I have to assume all the other variables as 0. Okay. So the first thing that you have to do to start solving. Okay. So if I have to start solving, then you have to assume initially everything is 0 and it is not being iterated. So we'll start with that. And then from there, you can take on the what is it, mental. So let us write down, assume everything is 0. Okay. Assume that solution is 0. Okay. So assume with a 0 solution, and then from the 0 solution, you can converge to the other solution. Remember, also very interesting is that even the global positioning system, the GPS, can also use this particular solution. Okay. Okay, fine. So let us try to write down a problem. So let us write down a small problem here. So let us write down this. I will write a diagonally dominant matrix here. 8x minus y minus 2z. Okay, let us first of all do with 3 variables, and so therefore we'll have some sanity here. So let us assume also that the solution. So let us see. I am going to assume the solution to be 2, 1, 1. Okay. So that means I'm saying this is the assumed solution, or rather in the system I should converge to this particular solution. 2, 1, 1. I'm saying that this should be the solution of the system, and I am writing the equations accordingly. All right. So just for the sake of understanding, that's what I'm trying to do. Okay, 8x minus y minus 2z. So now if I do that, if I substitute 2 here, what will happen? This will become 16, 16 minus 15 minus 2, 15 minus 2 is that is 13. All right, let us write another one. So I'm saying 2x plus 10y, okay, minus minus 1z, okay, so z, okay, minus z. Okay, so 2x, that will become 4 plus 10, 14 minus 1, and that will be also 13 here, no problem. And then I'll get the third equation. So let me write minus 2x and plus y, and I'm writing plus 15z, right like that. Then let us see what this equation will become. It will become minus 4 plus 1. It will become minus 3 plus 15 minus 3 plus 15. This will become 12. Okay. So let this be the system of equations, and I am going to write the alternative form of these equations, because if I don't do that, then otherwise I cannot solve. So what will be the alternative form of this equation? Okay, the alternative form will be x equals to 1 upon 8. Remember this, the coefficient of 8, x is 8, so 1 upon 8, and that will become 13 minus, all right. So then 13 minus plus y plus 2z. Okay, so I can do that. In the next equation, what will happen? This will become y equals to 1 upon 10, because 10 is the coefficient of y, 1 upon 10, and it will become 13 minus 2x and plus z. Okay, is it okay? And now the third equation, if I do z, and if I do that, then it will become 1 upon 15. Okay, and I'm going to write the other elements. 12 minus plus 2x, because y it is, this is 2x, and minus y. Okay, and then I can try to solve this. So at the initiation, what you should do is, at the initial instant, you will assume this everything is 0, and you will get these equations. First of all, you say you can start with x equal to 0. If I start with x equal to 0, y equal to 0, and z equal to 0, if I just start with these values, then what will happen here? If I start with x equal to 0, y equal to 0, if I put the values of y and z here, the first value of x comes over. What is the first value of x? Is 13 upon. Now, what happens here in y, please understand what will happen for y. Y will become 1 upon 10 into, okay, 1 upon 10 into, you have 13 minus 2 into the current value of x is 13 upon 8. Okay, and plus the current value of z, the decent value of z is 0. So this is what you have to do, and so you have to get, you are getting the value of y, a new value of y you are getting. So this is the newer value x new. Okay, so this is the newer value of y. This is again the newer value of y here, and you are going to use the older value of z for the newer values of x. So similarly, I'm going to if I do the z, then I'm going to substitute the new value of y into this particular equation. I'm going to get the recent value of z. So let us write this in Excel and see what happens. Okay. So for the sake of understanding, if is any can any of you actually note this down? So what I do is I will note this down for my own convenience at my in my notebook. I just do that because I just worked out this example in the board. So I'm going to write down so that when I'm putting things in Excel, I don't really need to come back here. Okay, so I've got x equal to 1 upon 8 into 13 plus y plus 2z. I got y equals to 1 upon 10 and the 13 minus 2x plus z. Okay, and here z will be equals to 1 upon 15 and then you'll get 12 plus 2x minus y. So this is what is there. We are going to move to a system where the spreadsheet will be loaded. So let me load the spreadsheet. So LibreOffice. Okay, so you can see the spreadsheet, I hope. All right. So in this Excel, so I'm going to say X. So these are old values, X old, Y old, and Z old. And here we are going to say X new, Y new, and Z new. Okay. So this is what I'm going to do. And whatever I'm going to do, I'm going to write the same equation. So what are these old values of x and y? Please see this. The old values of x and y, when we start this particular process, everything is 0. From this particular process, when I'm saying everything is 0, I'm going to now compute the new values of x. First of all, new values of x using the old values of x, y, and z. So new value of x. How do I do that? Remember, whenever I have to type a formula, I say equal. Okay. So now the formula says 1 upon 8. So I write 1 upon 8 here. Okay. And into 13. Okay. Plus no, 13 plus. Where is the y? Y is here. Okay. Plus 2 times. Where is z? This is z. Z is in C2. Okay. So what I have done is I have calculated the new value of x now here, 1.62. Okay. Now remember that the solution that we have assumed already is 211. Okay. So therefore, this method should converge to the solution 211. Let us see whether it converges or not. It might converge, it may not converge. I'm going to now compute the y new. So in y new, I am going to use the newer value of x and older value of z. Always remember that. Okay, so I'm going to do that. So I'm saying 1 upon 10, right? So 1 upon 10, and I'm saying into, all right. And again, I'm starting the bracket, so it will become 13 minus, now remember 2 into x, so 2 into x. So which x I am going to use? I'm going to use the newer value of x and plus z, I'm going to use the older value of z. Okay, so there you are. So you have got the newer value of y now into the system. So this is the newer value of y. Already you can see this is now 1.6 and the newer value is 0.975. Okay, and now this should converge to 2, this should converge to 1, and this should also converge to y. So now I'm going to calculate the new value of z. Again, what is the new value of z? Formula is okay, 1 upon 15 into bracket start, so it will become 12 plus 2 into x, 2 into, now where is the x? X is the new x, okay, and minus y, so this is the newer value of y. Okay, so if I do that, so you have got x new, y new, and z new. So you have already got values very close to the original solution. So I'm going to copy, remember, I'm going to copy these values, okay. So how do I do copy? Okay, here, and okay, here, and I'm going to say copy from here. Okay, so these are the old values now. And for the new iteration, remember, if I have to do the new iteration, just Control C here and Control V here. If I do that, you get the values. Okay, and I can keep on copying these formula, Command C, and then just do that, and you see what has happened here. After some time, the values have converged to the solution. Do you see this? Are you there?
Yes, sir.
Yes, sir.
So this has converged to the solution. You can take any diagonally dominant system of equations and try the same thing with the Gauss-Seidel method. This is going to happen. What is the mechanism? The mechanism is that you start with value 0, and then from 0 you start working out the newer values. And if you do that, then only this system is going to survive. If I what will happen, suppose for example I tell you don't start with 0, let us start with 100. Let us see what happens, है ना. हाँ, 0 से तो ऐसा हुआ, मैंने 100 कर देता हूँ, चलो देखता हूँ क्या होता है. देखो 100 फिर भी कन्वर्ज कर जाता है. देखो, look at this. Are you seeing this?
Yes, sir.
But if the system was not diagonally dominant, okay, इसको 1000 कर देते, let us do 1000, okay, 1000 और 1000, फिर भी कन्वर्ज कर जाता है. Do you see this? But if the system was not diagonally dominant, वो भाग जाएगा फिर. This is not going to happen if the system is not diagonally dominant. So please understand, this is how it is to be done, the Gauss-Seidel method. Okay, in the next lesson, we will talk about the Gauss-Jordan method and the Gauss elimination method. Those are very simple methods, and we will cover that in the next lecture. Okay.